The research paper discusses the current status of proton decay, a hypothetical form of particle decay where protons decay into lighter particles. It reviews both experimental results and theoretical models, including their predictions. The paper is organized into sections covering the definition of proton decay, its history, theoretical models, and future experiments. It highlights the significance of proton decay in grand unified theories and its relation to the Standard Model. The authors provide detailed explanations of key terms, concepts, and methodologies, including equations and algorithms, and summarize information from figures and graphs efficiently. They also discuss the limitations and assumptions of the current research and propose future work. The paper concludes with a personal summary and outlook. The research paper discusses the proton lifetime in the context of grand unified theories, GUDS. It begins by presenting lower bounds on proton lifetime in different decay channels, highlighting the importance of baryon number, B, and lepton number, L, conservation in the Standard Model, SM. The paper then delves into the concept of effective operators, explaining how GUDS predict exotic interactions through additional gauge bosons and scalars, which can mediate proton decay. Dimension 6 operators are emphasized, as they conserve B-L and describe proton decay through leptoquark gauge bosons. The paper also discusses dimension 5 and dimension 4 operators in SUSY GUDS, which can lead to faster proton decay. A key point is the dependence of proton lifetime on the GUDS scale and the gauge coupling constant. The authors derive a precise estimate of the proton lifetime in GUDS, considering assumptions about quark mass states, renormalization group running, and hadronic matrix elements. They also derive an upper bound on the proton lifetime for basic GUDS, highlighting the role of super-heavy gauge bosons. The paper concludes by discussing the implications for minimal non-SUSY and SUSY-SU 5 GUDS, noting that minimal SUSY-SU 5 is close to being ruled out by current experimental bounds. In the context of non-supersymmetric grand unified theories, GUDS, the paper discusses proton decay in various models based on the gauge groups SU 5 and SO 10. It starts with an SU 5 model studied in 2 works, including a minimal model with an SU 5 times U 1 PQ gauge group broken down to the Standard Model, SM, gauge group at the GUDS scale. The paper then moves on to SO 10 models, presenting 4 minimal non-supersymmetric models with intermediate scales described by gauge groups G, which are broken down to the SM in 2 steps. The predicted proton lifetimes are compared with current and best lower bounds from Super Kamiokande, SK, concluding that models B and D are allowed. Model C is partially allowed, and Model A is ruled out. The paper also reviews a minimal non-supersymmetric SO 10 model with an SU 5 gauge group as an intermediate scale, which does not achieve unification without threshold corrections. Finally, it discusses recent developments in proton decay in GUDS over the last 5 years, highlighting various models and their predicted proton lifetimes. This paper provides a comprehensive overview of grand unified theories, GUDS, focusing on their implications for proton decay. The author discusses the various types of GUDS, including minimal and non-minimal, SUSY and non-SUSY, SU 5, and SO 10 models. The discussion highlights the importance of experimental constraints on proton decay lifetimes, which have been significantly improved by recent experiments such as Super Kamiokande. The paper also reviews several GUD models that are still allowed by current experimental limits, emphasizing minimal non-SUSY SO 10 models as promising candidates. The author presents a detailed analysis of the predicted proton lifetimes for 4 such models, showing that they are compatible with experimental constraints. Furthermore, the paper summarizes the development of proton decay in various GUD models, including SU 5 and SO 10 models, and discusses the role of SUSY in these theories. It also highlights the potential of future experiments, such as Juno, Hyper-Kamiokande, Dune, and ES-SNUS-B, to further test these models and possibly detect proton decay. The paper concludes by emphasizing the importance of continued experimental efforts to probe the validity of GUDS and the need for theoretical models that can survive current experimental limits. The author suggests that minimal non-SUSY SO 10 GUTs are currently the most promising candidates for a unified theory of fundamental interactions.